So as I said in a previous video, the propagation velocity mu sub p of a wavelength measured in meters per second is going to be given as the product of the wavelength in meters and the frequency of the wave in hertz. And you could rearrange this. You could say that wavelength is equal to propagation velocity divided by frequency, or equally as valid, you could say that frequency is equal to propagation velocity divided by wavelength. And the point that I'm making here is that in both of these equations, something occurs in the denominator of the fraction, and therefore lambda and f are inversely proportional. As one goes up, the other one will decrease, and as one decreases, the other one will go up, is basically what we're saying there. And the only thing that's true about the limitations on wavelength and frequency of an electromagnetic wave is that they're fixed based on the material in which the electromagnetic wave is traveling. So if it's in free space, we know that the propagation velocity is equal to the speed of light, 3 times 10 to the 8th meters per second in free space. And mu sub p is going to be less than c in all materials. It'll just decrease. But other than that, there's no real limitation between frequency and wavelength. And so that provides us kind of a handy way to organize all electromagnetic phenomenon in what we call the electromagnetic spectrum. And what we will do is we will plot electromagnetic frequency and associated wavelength in a vacuum. So kind of make that a note there that these wavelengths are if the speed is c. So frequency of a wavelength is always constant. Wavelength of a electromagnetic wave will change depending on the material that the electromagnetic wave is traveling in. So this chart is for waves in a vacuum, electromagnetic waves in a vacuum. So what this thing is this electromagnetic spectrum. It describes all the possible EM wavelength frequency combinations of electromagnetic radiation. It also gives us some sense of the property of the EM wave, and that picture is just called the electromagnetic spectrum. And from the spectrum, we can see that EM waves, in terms of their wavelength, they can be smaller than an atom, 10 to the minus 12 meters, or that they can be bigger than a building, 10 to the third meters. And those long wavelength signals have a relatively low frequency, for instance, 10 to the fourth, and those very small electromagnetic waves, very small wavelengths, tend to have a very large frequency due to this inversely proportional relationship. We tend to use frequency to describe waves if they are below 300 gigahertz. And we tend to use wavelength to describe waves if the frequency is above 300 gigahertz. And the reason for this is historical. This tended to be the domain of electrical engineers, and this tended to be the domain of physicists and optics and stuff like that. So optics, they were more interested in wavelength, or their conversation was related to wavelength. And we engineers, we tended to use frequency because we were looking at electric circuits. So we can use the electromagnetic spectrum to kind of look at the properties of electromagnetic waves. And so I've got an EM spectrum here with just some notes that you can look at on your own. You can see that the EM spectrum on this one is increasing frequency here, the associated increasing wavelength here, and then we kind of tell you what those different bands of electromagnetic spectrum are used for. And you probably have already seen this in your communications courses, so I won't go into it in too much detail. But I will provide you with this material, with these slides, so that if you're interested more in the details of the EM spectrum and its associated uses, which I've written over here, that you can kind of go through those on your own time.